Good morning. I'm Prabha, Assistant Professor of Chemistry, PG and Research, Department of Chemistry, A.D.M.COLLEGE for Women, Autonomous, Nagapattinam. Today's class we shall discuss a rigid rotor quantum model. A rigid rotor quantum model, as we say, that it is an example for a two-particle system, and here we are concerned that it implies that there are two particles of masses m1 and m2 separated by distance d, and that is given by the r vector whose magnitude is equal to d, and thereby we have to apply the potential energy of the system there being equal to 0. In that cases, then we will consider how the Cartesian coordinates are being replaced by polar spherical coordinates. So for such a system of a rigid rotor model, where we take into account the two particles being separated or given by the magnitude of r vector as the diagram here states, and how do we arrive at the coordinates of m1, m2 and c. And here now, as we take into account the Schrodinger wave expression being given by, or how the Hamiltonian expression, where we take into account it is represented by minus of p cap square divided by 2 mu, where mu represents the reduced mass of the system of particles m1 and m2, and is given by the factor mu is equal to m1 into m2 divided by m1 plus m2. So first, then we have to define the wave function psi. So here, as we take, as we consider that the Cartesian coordinates as represented by x, y, z coordinates are replaced by polar spherical coordinates. So the psi wave function containing the coordinates x, y, z being replaced by r, theta and phi. So if this condition of transformation exists, so then the r coordinates are neglected from the Hamiltonian expression. So the Hamiltonian containing a second order differential function of the x coordinate and first order differential function of the coordinates as defined by that, and also containing the Laplacian operator plus summed up with the potential energy operator V of r. That expression we are reducing it in such a way that r coordinates are not neglected, for the reason that there lies no change in r vector, because this is equivalent to particles that are having masses m1 and m2 placed on a sphere, and it undergoes motion over there where the radius of the sphere does not have any change. Thereby, those coordinates that are containing r, in other words, we take that the equation that contains r can be, the terms that are containing r can be neglected, and thereby the first two terms being neglected over there, and hence it is being reduced, that which contains only the Laplacian. And now, and also in other words, we can take that since the particles of masses m1, m2 placed on a sphere of fixed distance r does not undergo any radial motion over there, and in other words also we can take that the kinetic energy that is associated because of the transformation or changes in r is not possible over there. We say that V of r, that is the r coordinate, being neglected, and that the wave function is defined only by theta and phi. So the wave function for a rigid rotor model being defined only by the polar spherical coordinates theta and phi. And now if we implicate that, we will consider that V, the potential energy wave function as defined by V of r, will be equal to 0, and that is a special case of V of r is equal to 0. So then, as we take into account the energy expression and reduce the Hamiltonian in such a way that it does not contain the r coordinates, it is thus done to eliminate the translational motion that is associated with the particle, and we are taking into account the energy associated only due to the rotational frequencies. So in such cases, we have to eliminate the translational motion, and that's the reason that why the r coordinates are eliminated from the Hamiltonian, and we have a reduced form of the Hamiltonian. Now we will apply Schrodinger wave equation such that h cap of psi is equal to E of psi, and we also establish that Hamiltonian is an operator operating on the wave function such that the eigenvalues correspond to the permissible values of the energy. So as we will substitute h cap, the reduced Hamiltonian, and also the wave function psi, which is represented by only the polar spherical coordinates theta and phi, that being equal to the energy expression, and the reduced form are having substituted and simultaneous operations in the equation will give the energy expression being equal to J into J plus 1 into H bar square divided by 2 mu D square. So these expressions contain J, where we implicate that L being replaced by J, or to solve this for the Schrodinger wave equation for a rigid rotor quantum model, to take into account the angular momentum quantum number L being replaced by J, and then its bar square, obviously this is different from where we take the values as being equal to NH by 2 pi, and the parameters that energy is dependent, or the rotational energy is dependent on, is nothing but the spacing between the J levels, or the angular momentum quantum number. So energy value is dependent on E, whereas to define the wave function psi we require, or it is dependent both on J as well as on M. The parameters of M is nothing but the Z coordinate of angular momentum. So as we take into account what are the permissible allowed energies of a transition, that will be delta J, that is given by the factor delta J, and delta J is equal to plus or minus 1, which is nothing but the selection rules for pure rotational transition. So always rotational transition associated with the vibrational transition also, but we take into account only the pure rotational transition thereby, and also understand the spacings between the rotational transitions, or the spacings are much more closer compared to that of the other rotational, that is the other transition that is also associated with, which is the vibrational transition that is associated with this. So the selection rules being equal to delta J is equal to plus or minus 1, and this energy expression contains the parameters of D and also the reduced mass of the system, D being the internuclear bond distances. So here, as we take into account the magnitude of R vector, obviously that actually defines the coordinates of the bond distances, or the internuclear bond distances. So now coming to the frequency of such an energy transition that is associated with that is given by J into 1 plus B into H, where B being the rotational constant, and the rotational constant is defined by H star divided by A phi square into D, and D from a knowledge of the moment of inertia. So here, as we take into account all these parameters, we just replace, having replaced the Cartesian coordinates by polar spherical coordinates, we just also explain the moment of inertia that is associated with the system, as we understand that I is equal to summation of mi into rho I square, mi rho I square. So for our two particle rigid rotor system, we take into account m1 rho 1 square plus m2 rho 2 square, and having the reduced form of the expression for moment of inertia being equal to mu into d square. Thereby the factor can be substituted in the energy expression as mu d square being replaced by the moment of inertia of the system, and hence the energy expression gets reduced to E is equal to J into J plus 1 into H bar square divided by 2I. And with the knowledge of the energy expression, we are able to assess the values of moment of inertia, and having known the moment of inertia of the system, we are able to assess the rotational constant B for a pure transition, and also with the knowledge of the rotational constant, it is possible to ascertain the internuclear bond distances between the two particles of masses m1 and m2. So the permissible levels of J being also, whenever energy expression being written over there, it has to be specified with the possible values of J. So J can take up the values as from 0, 1, 2 and so on, and thereby to ascertain the, or in other words, how the frequency of such energy transitions are associated with, you will understand based on the values of J and the spacings of J. Thereby the frequency corresponding to pure rotational transitions can take up as 2B, 4B and 6B, as the values of J increases, or the transitions from 0 to 1, 1 to 2, and 2 to 3, and so on. So in multiples of 2D. So that's a final rigid rotor model expression that gives an expression of the energy values and also to ascertain the moment of inertia. And having known that, an idea about the pure rotational transition, which are the selection rules that implies delta J is equal to plus or minus 1. And finally, the frequency of these radiations that corresponds to 2B for any of the transitions, that is a successive transition. So that explains a rigid rotor, which is a two-particle system that is concerned only with pure rotational transition, and the internal motion of such particles will be only the kinetic energy associated is taken only as being rotational, eliminating the translational motion that is associated with the